Good afternoon to everyone, and thank you for joining in for the another YouTube live discussion at the planetarium. On behalf of Nehru Planetarium, Nehru Memorial Museum and Library, myself Prerna Chandra, working as Program Manager, welcome you all for this YouTube live discussion. Today we'll be having discussion on the life of a star. To share more depth understanding on the stellar evolution, we have Dr. Sushan Konar with us. Planetarium, welcome you, ma'am. Dr. Konar is a theoretical astrophysicist by training. Her research activities have mainly centered on understanding the nature of the magnetic field in astrophysical compact objects like white dwarf and Neutron Star, and how the magnetic field influences the time evolution of such compact objects. She takes a keen interest in social aspects of the scientific community and has been the founder chair of the Working Group for Gender Equality of the Astronomical Society of India, ASI. She also devotes a significant time in education and outreach activity and is a member of the Public Outreach and Education Committee, POEC, of ASI. Moreover, she is also actively involved in writing popular science articles and maintains a weekly popular science blog at Sushan.Konar musing.blogspot.com. Planetarium, welcome you, ma'am, for giving your precious time to have discussion on this topic. Over to you, ma'am.
Thank you very much. I would like to express my gratitude to the Nehru Planetarium and Nehru Memorial Library and Museum for giving me this opportunity to talk to young people about the life of a star and share with them our excitement about such objects. So I will now share my screen. Welcome to all the people who have gathered to listen to this talk. So today I would like to talk about life of a star. Now, as you can see, the two words which are important in this title are life and star. Now, first of all, when we talk about the life of a star, it sounds a little bit unusual. Do stars have lives like living objects? Stars actually do have some kind of life, which we'll discuss today. And this is a beautiful picture of the huge galaxy that we reside in, the Milky Way Galaxy, which is home to a huge number of stars. This is visible from Hanle and taken by one of the astronomers there, Dorje Wangchuk. And as you can see, that this site, which we do not see from the cities anymore, but must have excited men in even in the beginning of the sentience, that is the of capability of intelligent thought of humans. So now over the centuries, people have tried to understand what these stars are and why different stars look different. What are their different properties? Do they evolve with time? And that's where the word life is relevant. So when we talk about life of any object, of human beings, we usually have a picture like this in mind. There is birth, and we begin from babyhood, and then we grow, and then grow old, and then at one point you would all die. So this is an evolution in time, and so this is how we evolve in time. So when we are talking about the life of a star, we are basically trying to understand how a star would evolve with time. Now, when we talk about the life of a person, we would also would like to know, becomes much more complete, the description becomes complete when we know what is the surrounding of this human being and the society or the place the person comes from, and so on and so forth. And what is most important is the question why. Why does a living being evolve? There are biological answers to that, and we would try to understand this why in the context of the stars. So now when we try to understand this why, we have to go to the beginning of physics. We have to go to the forces. Now we all know there are four main fundamental forces in nature: the force of gravity, the weak force, the force of electromagnetism, and the strong force. Now this chart basically tells you the particles that take place in these interactions are affected by these forces. And if you are not familiar with these objects, gravitons, bosons, etc., I would request you to ignore this column and look at the range. So gravitational force has an infinitely long range. Though with distance it decreases, but it has a long, very, very long range. Same with electromagnetic force. Both weak force and the strong force are very short range forces. And look at the relative strengths. This is very important. So as you can see that the strong force is the strongest force of all. And gravity is the weakest force of all. But all of these forces that are important for us are attractive forces, except for the strong force at very, very short range. And as you know, electromagnetic force is repulsive if the charges have the same sign. Except for that, these forces are attractive forces, and because they are attractive force, they help creating bound systems. And so as you can see that there are different kinds of systems which are bound by these different forces. And gravitational force, which we'll discuss today most of the time, binds large objects like solar system, galaxy, the planets, the stars, and so on. Now, as I have seen, the gravitational force and the electromagnetic force, these are the only two long-range forces. So beyond atoms, beyond nucleus, we do not have to worry about the weak force or the strong force. At long distances, only these two forces are important. And both of them have this nature which is called the inverse square law of forces. Both of them depend on the inverse square of the distance between these two particles. Now, for many of you, these form of the forces may look slightly unusual. I am writing the forces in CGS units. Most of you must be used to using SI units, but these are the forms in CGS units. Now, if I try to compare these two forces between, let us say, two protons, what I see is the force of gravitation between two protons is 10 to the power minus 39 times weaker than the electromagnetic forces. So therefore, gravitational force is completely insignificant when we are dealing with small masses. Only when this factor, this mass, this factor becomes large, only then we have to worry about gravitation. The specific characteristics, the important features of gravitational force is this is a universal attractive force, acts upon all matter, doesn't matter whether it is charged uncharged, what signature of the charge, it doesn't matter, acts upon all matters. And I understand that many people are interested in black holes. I would not talk about black holes in this lecture at all. But please remember that black hole is a system in which all other forces of nature are defeated by gravitational forces. So these are systems where the mass is so large that every other force is defeated by gravity. So now I have said we have bound systems because these forces are attractive. And when we talk about bound systems, we have to remember that in our school physics, we have learned that we are bound to the surface of the earth. We are not flying off in the space because of the gravity of the earth. So that's the gravitational force. But the fact that my hand is not moving away from my body, that is not because of gravitational forces. Or the atoms and molecules of this cup is not going away somewhere, is because of some other force. What is that force? That is the effective electrostatic force which binds all the everyday objects that we see around us. This is called a van der Waals force. The potential of this force look like this. People who are familiar with this potential description of a force, this is how the force look like, and it arises because all the objects, all the material is made up of atoms and molecules in which we have charged particles, protons and electrons and so on and so forth. So now when we are talking about this kind of objects, there is some interesting concept which will help us to go from this electrostatic binding force to the gravitational binding force. But because we have said that Earth is a gravitationally bound object and we are bound to the Earth because of the gravitational attraction. So consider some mountains. We have mountains all around us. Now there could be different kinds of mountains. One is a cliff face, very ragged kind of mountain, or you could have gently sloping mountain, or there could be artificial step pyramids. Given the hugely tall buildings that we are creating these days, so we can also consider them to be sort of pointy, sharply pointed mountains. Now, we all know that the tallest mountain on Earth is the Mount Everest, which has a height of about 10 kilometers. Now, the question would be, could we have had a mountain which is much more taller than the Mount Everest? Could we have something which is not yet discovered, maybe in the middle of some jungle somewhere, and which is 1,000 kilometers in height? Is that possible? We can give a theoretical answer to that. How? If the height of the mountain is h, we know the gravitational acceleration is g on the surface of the Earth, and let us say rho is the density of the material by which this mountain is created. So the pressure at the base of this mountain would be given by rho into g into h. Now the maximum value of h would be given by sigma divided by rho into g. Now what is the sigma? Sigma is the strength of the material at the bottom of the mountain. If it is too heavy, the bottom would break. It would not have the strength to support the mountain. So, as you can see, the gravitational acceleration, the density of the material, basically determines what is the maximum height of the mountain you are going to have on a given planet or such an object. And I would request the adventurous among you to go and do this calculation, I will give some references at the end of this talk. Do this calculation and check for yourself that there cannot be a mountain much taller than the Mount Everest. So that is actually close to the theoretical limit of the tallest mountain possible on Earth. Now, why is that relevant? Let us, for a moment, consider the shapes of these asteroids. This is a very small asteroid, somewhat like a sort of a very badly shaped cigar. This is going towards a spherical shape. This is reasonably spherical shape. So the shapes actually depend on size. What exactly is happening here? We call all these misshapen asteroids as potato asteroids, very aptly named. We can show that when the radius of such a potato is equal to the maximum height of the mountain on its surface, that is when the electrostatic binding force is becoming closer to the gravitational binding force. So gravity is now trying to take over, and that radius can be calculated in such a manner where G is again the universal gravitational constant, rho is the density of the material, and sigma, remember, is the strength of this material. So it so happens that if you do this calculation for all the asteroids are rocky objects, Earth is also effectively a rocky object. So if you put in appropriate numbers for this rho and sigma, what you get is for Ceres, which has a radius of about 500 kilometer, Ceres is about the smallest object in the solar system to be gravitationally bound. Okay, so this is how the systems are moving from the realm of electrostatic forces to the gravitational forces. So now anything larger than this Ceres would be gravitationally bound. So now when we talk about a gravitationally bound object, please remember I have said that gravity is an attractive force. Very good. Now if there is only gravitation, so everything should, there is an attractive force, it should collapse and everything should go to a black hole, right? So there must be something that supports the volume of an object by giving something against gravity. Now, how do I do that? We basically say that there is a pressure which acts against gravity. Now, what is the gravitational pressure? Let us do a very simple-minded calculation. Let us say we have a sphere of mass m and radius r. We can think of this as separated into two hemispheres. The distance between two parts is about r, the radius of this object. Please do not be confused by this picture. The two halves of the hemisphere are not separated in space as such. I am just showing you how this should be. So this is a sphere, and the mass of each of these parts would be m by 2. So the force of gravity between these two parts of the hemisphere would be gm square by r square. Gm into m by r square. There will be a small numerical factor in front which I have ignored. Now consider this surface. The surface area of this is pi r square. So therefore the pressure acting on this each surface would be roughly equal to gm square by r to the power 4, and that is the pressure at the center of an object which is gravitationally bound, has a mass m, radius r. So that is the pressure due to gravity, and now we need some other pressure which would act against gravity to keep this object stable. So this is another way of saying the same thing. We have a gravitationally bound object. Here it's a schematic of a star. So the pressure coming from something is, these are these red arrows, it pushes out and gravity pushes in. Now we have two reservoirs of this pressure. What is there? For example, consider a star. It is made up of gas and it has a temperature T. The gas pressure would be proportional to the density of the gas and the temperature of the gas. Those of you who have studied Boyle's law in thermodynamics would be familiar with this. So there is a gas pressure. There would also be the pressure of the radiation, because we have, the light, the heat inside a hot object, and so that pressure depends on temperature as T to the power 4. So what I see here, what is important is, in order for the star to hold gravity off, that is to be in equilibrium with a particular size, what is important is temperature. So it has to be hot. And we know the closest star to us is sun, and it's a very hot object. We get sunlight coming from it has a temperature. So this is what is keeping a star in equilibrium, and this is known as, in technical terms, hydrostatic equilibrium. So what happens when these two are equal, these two forces are equal, they are, it's hydrostatic equilibrium. If, for example, the gravity becomes larger, like in this case, this is equilibrium, when the pressure due to the gas and radiation becomes larger than the gravitational pressure, then it expands. When the gravity is larger than the outward pressure, then the object would contract because gravity is pulling it inward. And when such a gravitationally bound object contracts, what does it do? It releases energy and the temperature increases. Now this is the process which is very, very important in the life of a gravitationally bound object, in particular the stars. That gravitational contraction releases energy and gives rise to the increase in temperature of that object. Now we will use that concept in a while. Before that, let us now look at the structures that we have talked about so far. So these are the small scale structures. So we have already said that potato asteroids and many of these terrestrial planets, they are basically electrostatically bound, or just about at the limit of electrostatic binding, moving over to gravitational binding. Then we have failed stars. Why do I call them failed stars? I will explain in a moment. These are the giant planets, not the terrestrial kind of planets like Earth, Mars, Mercury. These are giant planets which are also called Jovian planets like Jupiter, Saturn, the gas giants, and brown dwarfs. Then we have the stars, and then we have the stellar remnants, the object that is left behind after a star has died. What is the star death? We will talk about it. So we have white dwarfs, neutron stars, and black holes. And you will notice that I have not talked about larger structures, that is the solar system, the galaxy, etc. All of them would be in any case gravitationally bound, and in this particular lecture we would not worry about it. So first of all, let us talk about the failed stars. What are the failed stars? mass is less than 80 times the mass of Jupiter. And I'm sure some of you know that the mass of Jupiter is about 0.001 of the mass of the Sun. This symbol stands for the mass of the Sun. Now, there are two types giant planets where the mass is less than 13 times mass of Jupiter, and there are brown dwarfs between these two limits. Now, you will see that I have said giant planets have no fusion and brown dwarfs have D2 fusion. I will explain just in a minute. And then there are the stellar remnants. And we will talk about the stellar remnants towards the end of this lecture. So here we have Jupiter. This is a gaseous object and supposedly has a core of rock, metal, etc. But this is basically hydrogen in a metallic state. So hydrogen is so compressed, it behaves like a metal, and it is the pressure of this metallic hydrogen which supports it against gravity. Please remember, every time we talk about a structure, we have to always talk about what is holding it against the constant pull of gravity. Now we have the brown dwarf. Here are the Jupiter-sized planets. Here is Earth, Jupiter-sized planet, and brown dwarfs. This is a small star, and that's our Sun. We'll talk about the star in a little while. In brown dwarf, what we have is a incomplete burning of hydrogen to helium. What do we mean by that? I will talk about that in a little while. But in brown dwarf, it starts to, or it tries to become a star. So now we are getting closer to saying what is a star. It starts hydrogen fusion, converting hydrogen into helium, but it doesn't, there are several steps. It cannot complete the steps, and therefore it is not yet a star. So therefore, what is a star? A star is something where hydrogen is converted into helium. That is the basic definition of a star, an object in which hydrogen is converted into helium. So now we have come to the stars. These beautiful pictures of molecular clouds, these are called nebula. These are basically the birthplaces of stars. These are called star forming regions. As you can see, they're really beautiful pictures, and they have interesting shapes, and of course we have given appropriate names to them. This is my most favorite nebula. As you can see, it really looks like a head of a horse. So how does a star form? In such molecular clouds, which are huge molecular clouds, these clouds, because of the force of gravity, they collapse and they fragment. So this big cloud then fragments into smaller clumps, as are shown in this picture. Now these clumps again collapse and fragment, and they make something called a protostar. It's not yet a star. Protostars again collapse. Now please remember, I said that every gravitational collapse is associated with heating. So the temperature is rising. And please remember, the universe is made of hydrogen. So we have this gas of hydrogen which we are continuously heating. As you continuously keep heating hydrogen, when we get to the temperature of about 1,000,000 degrees, then hydrogen start, different hydrogen, by this time they are not hydrogen atoms. Hydrogen has become ionized. A hydrogen atom is basically a proton and an electron. So when the temperature rises, these atoms collide with each other, electrons are thrown out of these atoms. So we have ionized hydrogen. What is ionized hydrogen? Hydrogen atom without an electron, which is basically a proton, a bare proton. So this is important to remember. This is the structure of hydrogen, very rough structure of hydrogen, and this is roughly the structure of a helium. Helium is the second element in the periodic table. All of you know that. It has 2 protons, 2 neutrons in the nucleus and 2 electrons outside. So now what is happening is hydrogen becomes helium. Now a helium nucleus has 2 protons and 2 neutrons bound together. Now if I take a look at the mass of these individual nucleons, I have 2 protons and 2 neutrons, and so the mass is 2 mp plus 2 mn. Now if I compare this to the mass of a helium nucleus, this 4 stands for the number of nucleons it has in the nucleus. I see that there is a difference in mass, and this is called the mass defect, and you all know the famous E equal to mc squared formula. So this mass actually comes out as this little mass that is lost. It's not lost, it comes out as the energy, and that is the energy we come from hydrogen converting into helium. That is the energy which is the source of energy of all the star. This is called nucleosynthesis. From simpler elements, more complex, larger elements are being formed. Now, we have said that universe is full of hydrogen, and hydrogen gets ionized, and we have protons, but helium has protons and neutrons. Where did the neutrons come from? So these are the steps which is called the simplest nucleosynthesis reaction. It's called a PP chain reaction. So I have 2 protons, they collide, they form some sort of a bound state which is temporary. Then one of the protons convert itself into a neutron. Now neutron doesn't have a charge, proton had a positive charge, so this amount of positive charge has to be, you have some positive charge here. On this side of the equation, you cannot simply destroy the charge has to be conserved. So a particle comes out with a positive charge. It's very small mass of this particle. This is actually anti-electron. It's like electron has a positive charge, and I'm sure all of you know this is the positron, and some energy also goes out, and that is carried by something called a neutrino. It's a small chargeless particle, it carries away energy. In the second step, this PN, this bound state, this has a name. As you can see, this is again a hydrogen, but a hydrogen with an extra neutron in the center, and this is called a deuterium or heavy hydrogen. So now this one collides with another proton and forms a bound state which is PNP, 2 proton, 1 neutron. So this object, as you can see that there are 2 protons, so therefore this is helium, but this is a 3 helium. It doesn't have 2 neutrons, so therefore the atomic mass is only 3. This is called a 3 helium, and then it combines with another such 3 helium, forms a 4 helium, that's the final product, and leaves out 2 protons to start the reaction over. So this is the entire process of nucleosynthesis, from going from hydrogen to helium. And what happens in brown dwarfs? In brown dwarfs, it stops after this step. So in brown dwarf, only this step happens. So it creates heavy hydrogen, that is the deuterium, and it ends there. It cannot go up to helium. Now you will ask me the reason why this is happening. What is the difference? Why some stars cannot become stars and they remain brown dwarfs, and then there are some stars? It is all dependent on mass. You remember that I said that as there is gravitational contraction, energy is released, temperature rises, and the gravitational energy, which is proportional to the m square, the square of the mass of this object. Therefore, the energy also should be proportional to the square of the mass of this object. The heavier the object, the higher the temperature, and the higher the temperature, the higher the probability of this reaction completing, because all the steps, as you see, step 1, step 2, step 3, it requires higher and higher temperatures to complete. So brown dwarfs are objects which do not have adequate amount of mass, and they finish their nucleosynthesis after this first step. They do not have appropriate amount of temperature to go to the next step. So only objects which are heavier than 0.08 solar mass, they would start becoming stars. In other words, those are the objects which would be able to complete this reaction. Now, for heavier, much heavier stars, the conversion from hydrogen to helium goes via much more complicated nucleosynthesis reaction chain, and this is called a Sienna cycle or Sienna chain, where this reaction happens in presence of carbon, nitrogen, oxygen. Now you will ask me, we only have hydrogen and helium, where do these things come from? These have come from earlier stars, and the trace elements are present in the stellar material, and they act as catalysts. So finally these things will stand by and would be as before, but in the process hydrogen would be converted into helium. And this process happens only in very, very massive stars. So what happens for a small star when hydrogen burning ends? You know, there is only that much hydrogen which converts into helium. What happens? In the center, then, initially the maximum temperature would be at the center, of course, and initially the burning happens there, and when hydrogen is converted into helium, burning stops there, then the burning would start happening in the outer region. And this core region, because there is no active energy generation, but the radiation is going out, it starts to collapse again, because again gravitational pressure is pulling it inwards, and because the temperature is not adequate to support that gravitational pressure, it starts collapsing. So then what we have is a situation in which the helium core has collapsed and the envelope has expanded, and it has a hydrogen burning shell. Hydrogen is still burning on the outer shell of the core, and because radiation has come out, the envelope expands, it becomes redder, and this is the red giant phase of a small star like our sun. Our sun is a small star. It's not a very massive star. So when sun completes its hydrogen burning in the core, it would become a red giant. The diameter of this object would be twice the astronomical unit. I'm sure you know what is astronomical unit. It's a unit of distance from the sun to the earth. So basically, when the sun becomes red giant, it would swallow the orbit of the earth. And compared to the present size, it would be the present size of sun is actually 0.01 AU. So 1% of what it would be as a red giant. Now, before I come to this, let me say something. Sun would not do anything after making helium, but more massive stars, what would happen as the core collapses and starts becoming hotter and hotter, it would reach a set of temperatures where we could have helium burning. What is helium burning? Helium goes and converts itself into carbon. And that is this reaction. So it's called a triple alpha reaction because the basic nucleus of a 4-helium is also called an alpha particle. So 3 of these alpha particles, 1, 2 and 3 here, they would finally combine to give a 12C. You remember carbon has 6 protons and 6 neutrons in its nucleus, so therefore it's 12. So helium burning would give us carbon, and this would happen in a much heavier star. So what happens, here is a sort of comparison between what happens in a low mass star and a massive star. After the hydrogen burning has finished, in a low mass star, what we have is a helium rich core. Hydrogen has burned and helium has been generated. Then what we have is a hydrogen burning shell. In this region, temperature is still large enough and there is hydrogen. So there is hydrogen burning shell, and this is the expanded hydrogen rich outer envelope. So this is a low mass star on the red giant branch. For a massive star, what happens is, after many more stages of nuclear burning has happened, in the core we have oxygen, neon, magnesium, etc. Then we have a carbon burning shell, then we have a helium burning shell, and then we have a hydrogen burning shell. So in more and more massive stars, we may have many shells burning various nuclei. Depending on the mass of the star, we will have different number of shell burning components. And whereas a small star goes into a giant, which is called a red giant, for massive star, they become much bigger and they are called red supergiants. They could also be blue supergiants, forget about that. So they would go into a supergiant phase. Now, would this go on? We have a huge periodic table. Would it go up to uranium? No, not really. This chain reaction would stop at iron. Why? Because look at the binding energy. So here the mass number increases in this direction and binding energy per particle, increases in this direction. So we have hydrogen and helium and carbon and etc. and etc. So when we are coming from hydrogen to helium to carbon and etc., the binding energy is decreasing. So if the binding energy decreases, that means when I go from hydrogen to helium to carbon, I can extract some amount of energy. But after iron, the binding energy increases. So then I cannot extract binding energy anymore. If after iron if I have to combine two iron atoms, two iron nuclei to get to a more heavier nuclei, I have to give energy. And that is not very useful, and that is not what would keep the stars shining. So the reaction basically stops when this nucleosynthesis reaches iron, and that is when the stars are going to complete their nucleosynthesis. And this is roughly the story of the stellar evolution. It basically depends on mass. Now this line on a diagram, which is temperature versus luminosity, energy generation, that is the luminosity. This line is the main sequence. What is main sequence? The time when a star is burning hydrogen to helium. And that is called main sequence, and that is where the stars spend the maximum amount of their time. Then after that has finished, after hydrogen burning at the core is done, the smaller stars, and by the way, this line from bottom right to the top left is this goes in increasing mass. So here are the smaller stars and there are the bigger stars. So the smaller stars, when they turn off from this main sequence line, they go into the giant phase, and when the larger stars turn off from the main sequence line, they go into supergiant phase. And this diagram is known as Hertzsprung-Russell diagram, after the people who are responsible for this diagram. This track how a star moves in this Hertzsprung-Russell diagram is determined by the mass of the object. And higher the mass, the faster a star moves on this diagram. So now we have finished nucleosynthesis, and the star does not have any more source of energy generation. What does the star do? The star dies. How does it die? If it does not have any more source of energy generation, then gravity must take over. But gravity does not take over in all stars, is not able to take over in all sorts of stars. This is what we get as are called stellar remnants. When a star is dead, that is, it is no longer going through nucleosynthesis and generating energy, the object that it leaves behind is called a stellar remnant. So the smaller masses, when I say mass of the star, please remember, one is always talking about the mass at the main sequence, because when it turns off from the main sequence, there is a lot of other processes go on and it sheds mass and various other processes happen. So when one talks about the mass of the star, one is talking about the mass at the beginning of the main sequence. So here is a scale in the units of solar mass. The stars which start with a mass of this range, 0.08 to about 8, after the main sequence they go into a red giant phase, have a planetary nebula which is the expanded envelope, and finally the core region becomes a white dwarf. And the mass of this core of the white dwarf, the maximum mass of a white dwarf is the limit given by Subramanian Chandrasekhar and is known as the Chandrasekhar limiting mass, which is shown as MCH. Now, for objects which start with a main sequence mass of 8 to 25 solar mass. After the main sequence, they would go to a giant phase, a supergiant phase actually, explode in a supernova, and would leave behind a neutron star which has a mass of 2 to 3 solar mass. And for even heavier objects, even heavier stars, after supernova, they would leave behind a black hole. Now, what is the difference between a white dwarf and a neutron star and a black hole? Black hole, in white dwarf and neutron star, what happens is they have a structure, and therefore something balances the gravitational pressure, and we will see which kind of pressure balances gravitational pressure. Black hole does not have a physical structure. Why? Because there is nothing, it is so massive, there is nothing that can hold gravity, and it collapses. So it's a completely collapsed stage, and therefore this is a very, very different kind of object and has very different kind of physics governing its dynamics. In this particular talk, we would only talk about white dwarfs and neutron stars, which still has structures. Now, I'm sure all of you have seen the Orion constellation in the sky, and you're familiar with the star which is known as Sirius, or the dog star of the hunter in the Orion. Sirius is a binary star, meaning it has a companion. The companion is a white dwarf, and therefore it's very small, it's not seen, but next time you look at Sirius, you should know that it has a white dwarf companion. What happens in a white dwarf is the pressure of gravity is balanced by the pressure of quantum degenerate electrons. Electrons are in a particular state similar to the state they are in any metals that you see. They are in the compressed state of white dwarf. Why compressed? Because, please remember, the mass is about half to 1.4 solar mass. A solar mass is 10 to the power 2 into 10 to the power 33 grams. A million times that of the mass of the Earth. But the radius is about 10 to the power 4 kilometer. So the radius is roughly the same as the Earth's radius. Something which has mass a million times larger and the radius similar to us has much larger density, of course, and therefore it's a very compressed state. And the electron density is very, very high. At such high densities, electrons have a particular property and has very high pressure, and that is the pressure which holds off the gravity in case of white dwarfs. And because of this compressed state, it also has very, very strong magnetic field, and that gives rise to certain interesting physics. So white dwarfs are essentially like crystalline solid of heavy atoms. And here is the mass radius diagram of a white dwarf. I wanted to show you because you see, as the mass increases, the radius of a white dwarf decreases. That's the characteristic of the electron degeneracy pressure. And there comes a time, there comes a mass at which the radius goes to 0. This basically tells you that that is the maximum mass a white dwarf can have. It is not possible to have mass higher than that. If it acquires more mass, it would collapse to a black hole state. The second kind of remnant are the neutron stars. Neutron stars have a very, very exciting and rich history. People who are interested should go and look at such history. These were theoretical conjectures given by Landau, Bode and Zwicky in the 1930s. And finally, it was discovered in 1967, which came in a paper published in 1968. So you see, almost 40 years before they had discovered, people from basic theoretical considerations gave the conjecture for neutron stars. And for Landau, it's even more interesting. You should go and read how Landau's conjecture for neutron stars was almost at the same time when neutrons were being discovered. People didn't know about neutrons before that. So the mass is, as I have said, about 1.5 to 2.5 solar mass. Radius is 10 kilometer, like a small city. So of course the densities are much higher. Magnetic fields are very, very large, and they have very fast spin period, from millisecond to about 1000 seconds. And the pressure is this time supported by the degeneracy pressure of the neutrons, similar state like electrons that we were talking about last time, and nuclear force. Please remember, I said at the very beginning that nuclear forces become repulsive at very short distances, and we are talking of very short distances because the matter is squeezed here. So that repulsive part of the nuclear force now gives a fight to gravity. So this is what gives a neutron star, allows a neutron star to maintain its structure. Neutron stars have very extreme physics. As you can see, the density is like the density of an atomic nuclei. So it's like a huge nuclei in the sky. Because of the compact structure, there are general relativistic effects. People who are familiar with general relativity would notice that has very, very fast rotation. As I said, it can rotate at millisecond period, and the maximum spin period for Earth, if you calculate, we rotate at 24 hours per day, but that is not the maximum, the minimum spin period for Earth, the fastest rotation that Earth can have. I'm sorry, this should be P min. The minimum spin period for Earth is about 10 to the power 5 seconds, a few hours. High density has other physical consequences which I would not mention because many of you would not be familiar with superconductivity, but this does give rise to very, very strong magnetic field. And how do we know about these neutron stars? These behave like radio pulsars, and what we see is here is Earth, and here is that distant neutron star. This is an artist's impression, and it's sending regular pulses of energy in radio, in optical, in X-ray, in gamma ray. So we get very regular periodic pulses from these objects that are detected in our observatories, and there are various properties associated with these pulses from which we can infer that they are coming from neutron stars. So basically this is the structure of the neutron star that gives rise to these very periodic pulses. So there is a small object, 10 kilometer object, and it's rotating very fast. It has a magnetic field which is not aligned with the spin axis. So it's like a bar magnet which is rotating very fast with a tilted axis. So that gives rise to this interesting phenomenon. Till date, we have discovered almost 3,500 neutron stars, and I show this picture just to tell you that they have a huge range of magnetic field. The magnetic field goes from 10 to the power 8 Gauss to almost to 10 power 16 Gauss, and the spin period goes from a millisecond to about 1000 seconds. This is the zoo of neutron stars. We'll ignore that. One small point that I want to talk about neutron stars before we finish. So neutron stars are, as I said, very, very compact, very high density object. So in the crust, in the surface region of the neutron star, we get to see very peculiar atoms. Now, we know that on Earth, the atoms, the smaller atoms in the nucleus of them, the neutron is to proton ratio is about 1:1. So here, this is the number of protons, that's the number of neutrons. Near, the very small ones, helium, carbon, oxygen, nitrogen, the number of neutrons and protons are more or less 1:1. This cyan band is all the nuclei, all the atoms that we know on Earth. Why it's a white band? Because all of you know that we have isotopes. There are, as we have just seen that there is hydrogen, there is heavy hydrogen, so there are other isotopes for various elements. Now you see the kind of atoms that we see on the surface of the neutron stars. For example, this is tellurium, which has 52 protons, 150 neutrons. This is way off. I'm sorry. And we do not see anything like this on the surface of the Earth. So what is happening is, in neutron stars, we have nuclei which has too many more neutrons compared to what we are familiar with on the surface of the Earth. And that gives rise to a very, very interesting phenomenon. This is a periodic table and telling you where these elements are coming from. These blue ones are coming from Big Bang fusion, when the universe started at Big Bang. And nucleosynthesis at Big Bang gives rise to basically hydrogen and most of the helium. Then dying low mass stars like our sun, these are these yellow ones, and then consider this bit, merging neutron stars. You know that in last few years through the gravitational wave observatory, we have detected neutron star mergers events, and we have seen that most of these heavy elements are coming from when two neutron stars merge together. So most of the important elements that are required for life, like carbon, nitrogen, etc., they are coming from dying low mass stars like our sun, but heavier element like gold, platinum, etc., they are coming from the merger of neutron stars. So merger of neutron stars is very, very important event in the life of the universe. The supernova explosions and these exploding massive stars, so basically standing for supernova explosions, also the exploding white dwarfs. So supernova explosions and merger of neutron stars are basically primarily responsible for giving us the heavy elements of the periodic table. So that is an important astrophysical event which is responsible for all the interesting things that we see on Earth, because different elements are required for all the interesting phenomena of life that happens on Earth. So otherwise, this is a size comparison of the objects. So this is Betelgeuse. Betelgeuse is in news these days very much. It's a red giant. Compared to Betelgeuse, sun is like this, a white dwarf is like this, a neutron star is like this, and the black hole is actually a point. Now I have not talked about black hole. This is an interpretation by the famous cartoonist Sidney Harris. It's black and it looks like a hole. I would say it's a black hole. I would not really say so. I would only say that I am not an expert to talk about black holes, so I am going by this cartoon. I really do not know much about black hole. What I want you to go leave this lecture with is this statement, which is my favorite statement. A neutron star is the last line of defense that matter throws up in its hopeless struggle against gravity. Okay, so this gravitational attraction, which is omnipresent, and the more massive the object, the stronger is the gravitational attraction. And neutron stars are the last line of defense, in the sense that that is the most squeezed state of matter because of gravity. After that, it's a collapse to black hole. Now, I wanted to finish this lecture by spending 1 minute on people who are interested in astrophysics or probably look for career in astrophysics and astronomy. And I want to leave this, observation from my side to the youngsters. If you want a career in astronomy and astrophysics, please learn your science, learn your mathematics very well, learn your physics, and learn logical reasoning. Continuously ask the question, why? Why this happens? Why this happens? And even for science, you need language skills. That is one thing that we see that many people ignore. But doing science does not mean ignoring language skills. You would need language skills to say what you are doing, what you have found. So that is also very, very important. And please, science learning is not about information collection. Please ask why. And if you want to do astrophysics and astronomy, it is absolutely not necessary to collect astronomical information. Please learn your mathematics and physics, and that would be enough. So I would leave with some further readings. Here are two papers, people who are adventurous to estimate the height of Mount Everest. Please look at that. This series that I wrote in 2017 is about structures, smaller structures in the universe. And if you really want to study about stars and the compact stellar remnants, please go and buy these two books. They are reasonably inexpensive, very, very inexpensive actually, and they're excellent. So thank you very much for listening. I would end here. Thanks a lot.
Thank you, Dr. Konar, for sharing this presentation with us. So now the session is open for the questions. Our black hole is way to another universe. Is multiverse hypothesis true?
Okay. These are questions that we do not yet know answers to. No, black holes are not another way to another universe, not in the sense of popular science fictions. And the multiverse hypothesis, it's a hypothesis till now. There is no definitive proof for or against it. Yes.
I have heard that much more massive star may undergoes nuclear fusion beyond iron, but don't know the specific conditions.
No, that is not correct. When you say much more massive stars, you please remember that the stars, the maximum mass of main sequence stars is about 100 solar mass or so, and there is no way a nuclear fusion can go unassisted nuclear fusion. That is not non-artificial natural nucleosynthesis, nuclear fusion can go beyond iron. As I have shown that in the plot, if you have to go beyond iron, the reaction becomes endothermic instead of exothermic. It means you have to provide energy in order for that reaction to go ahead, and that does not happen, that cannot happen. So therefore nuclear fusion beyond iron does not happen in nature.
Next we'll take Arna Chakravarti. Ma'am, which state of matter is a black hole actually in?
It's not a state of matter. As I have said, matter as we know does not exist inside a black hole. There is no matter. It's a collapse state.
How are we so sure that black holes exist? They can be Planck star, measure of Planck length too, and can mimic black giants.
I do not think what you are asking is appropriate, because there's nothing called black giants. I do not know what exactly you mean by black giants. And when you say how are you so sure that black holes exist, the black hole in the center of a galaxy has actually been observed. Now you cannot directly observe a black hole. There are indirect signatures of the black hole which you can theoretically calculate, and then what you observe you match with that theoretical calculation. So something called an event horizon telescope, it's an instrument which has detected a massive black hole at the center of the galaxy a few years ago, and we have a definitive observational proof of a black hole.
I have a question that why nuclear fusion in the star occur first. I think we have taken this question. No?
I have actually said it in within the talk, but why it happens inside the core, because there is, as you can guess, that there is a temperature gradient inside the star. So the maximum temperature is at the center, and then it drops radially outward. So therefore the maximum temperature you will get at the center. So the appropriate temperature for any particular nuclear reaction would be achieved first at the center, and then as the temperature increases, then in the outer region. So the nuclear fusion would first start at the core.
So more other questions on the black holes actually. Does black hole exist?
As I have said, just in
Yes.
answer to a previous question, yes, they do exist. We have observational proof of that now.
So, participant, you can drop your questions in the chat box so that we can pick it because I think the earlier question I have already taken. If anybody's question left, you can send that question again so that I can pick because so many conversations are coming. So one of the students is interested, ma'am, about the black holes. What do you think? What is your comment on that?
Uh,
Black
no,
holes exist or not?
as I have said, they exist and we have seen them. So,
So he's written, okay, ma'am, I understood. Thank you so much for the explanation.
okay.
So thanks for the understanding. Thank you. I think with this, we'll wrap up the session because the questions drop in the chat box we already taken.
Okay.
One of the student is also writing. Nice. I understand now. It is clear.
Okay.
So with this, we'll wrap up the session. And if any questions left out, you can definitely send us at the planetarium so that we can get back to you on this. Thank you, Dr.
Sure.
Konar, for giving your precious time and sharing this presentation with us on the YouTube channel. So in case any students want to ask something, they can drop on the email ID of Nehru Planetarium so that we can get back to you on this. And thank you for joining in. And we really hope to see you again in another live session of YouTube at the planetarium. Thank you so much. Thank you, Dr.
Thank
Kumar.
you, thank you so much, and thank all the students who have been tuning in and listening, and thank you very much.
Thank you.